Well, welcome back to the main room, everybody. We are so excited that you are here to for our Q&A and wrap up for our clean water event. Today we have for our Q&A and our clean water event, we have two amazing college engineering students who are going to introduce themselves, and then we're going to incorporate Joanna, and then it's going to be your time to shine. We're going to spotlight you and let you share out with your designs. But I'm going to stop speaking, and Sinai, if you are ready, I see you are here. You can take it away.
Yeah, hello everyone. My name is Sinai, and I am a current senior at Cornell University studying environmental engineering, as well as pursuing a master's in mechanical engineering. And my interests really lie into like biotech, biomechanics world, and then as well as renewable energy, sustainable development. And yeah, I was this past summer I was a summer intern for Engineering Tomorrow, and I've helped a lot of data or developed a lot of data in Salesforce, and also worked on a lot of labs with wastewater and agriculture. And well, I'll pass it on to Grace. Oh, sorry. So yeah, so
I think, did she freeze for everybody?
She's frozen for me.
Okay, so Grace, you can take it, and we'll get back to Sinai in a minute.
Okay. I will move through. Okay. So hi everyone, my name is Grace. I am a senior at Dartmouth. I'm majoring in mechanical engineering and I'm minoring in human-centered design. And specifically within engineering, I'm super interested in construction management. So this means being on site, being on your feet. I hate sitting at a desk all day. And so it's super fun to, walk around sites and see things being built in real time. I'm also super into MEP design. So MEP stands for mechanical, electrical, plumbing. And these are basically just the systems that allow buildings to function and allow people to use them in their fullest. And then finally, I'm super into sustainable building. So, thinking of really green and innovative solutions that ultimately are less harmful for the world around us. So that's a little bit about me. Now I'll just go into my path, some things that I have gone into from high school until now. So in high school, I was part of an engineering and architecture design program. So very similar to Engineering Tomorrow, actually, where I kind of got inspired. I got to see what engineering really was. And that's why I'm pursuing it in college now. I also was in the newspaper club. I volunteered for the Boys and Girls Club, and I was a big athlete in high school and also in college. In terms of internships, I interned for ME Engineers as a mechanical engineer, working on the design side of construction. And then I worked for AE Competition as a construction intern this past summer. Again, right now I'm at Dartmouth doing mechanical engineering, and some things I'm involved in here just include, some research. I'm a TA, so I help students with their coursework. I'm an ET college mentor. And I work for the Dolly Lab as a designer and project manager, which is really awesome. And I'll go into that next. And then going forward, I luckily have a full-time job, which is exciting. In August, I'll begin my full-time position with AE Competition as a project engineer. And I'm working specifically in the healthcare sector of construction. So things like hospitals and things like that. So that's a little bit about my path, and I'm happy to answer any questions about this after we're done walking through. And then here are just some photos. There's me in the bottom left corner at the MetLife Stadium in New York with ME Engineers. So that was a super cool experience. I'm in the dugout working on some electrical engineering stuff. So there are some really cool sides to engineering. Then I have some of my Dolly work here in the upper left, and that, phone computer app looking thing. We do a lot of AR, VR projects and just mobile app development, which is really fun to be creative. And then I have some bridge designs there. There you can see some sketches, the very early stages of building something, and then our actual prototype, which was pretty successful, and that was exciting. That was for a class. And then in the middle here, you can see a crazy looking diagram. That was a solar water heater that I designed with some Dartmouth students that's actually in place and sort of working in Uganda in Africa right now. So that's super exciting. So yeah, that's a little bit about me. I don't know if Sinai is back on.
She is back.
Okay, let me
Yes.
backtrack. Okay.
So sorry, guys. My computer keeps restarting all day, but starting again. So yeah, through high school, I joined a lot of STEM programs and build my engineering background that way. And I started interning at companies like DoorDash, and Cymergen which was like a biotech company. Coming into Cornell, I knew I wanted to do sustainability, mainly in wastewater treatment. So I joined a project team here at Cornell called Agua Clara, which their mission is just to provide sustainable water resources in countries in Honduras. And with that manufacturing kind of side and kind of mechanical engineering classes that I took, I was able to land an internship at a biotech startup. And there I really honed my experiences in engineering overall, but also created a new passion for mechanical engineering and biotech as well. So that's where I decided to go into a master's for mechanical engineering and go into the manufacturing and the biomedical field as well. And in terms of like visual trajectory, so on the top left, you can see a lot of engineering procedures. On the top left, most right, or top left most photo is me presenting an engineering project at a consultation, and then as well as having worked with other people, and as well as presenting different projects. On the middle or kind of right top is my work with Agua Clara and doing a lot of manufacturing with some of the wastewater treatment at the wastewater treatment sites and some of the machinery there. So definitely has different components to engineering there. And on the bottom mostly is just a lot of biomed and analysis lab work that I've done. So right now I am currently working at a lab here at Cornell in terms of like biomechanics and of ligaments and bones. So that's very interesting and something very new and exciting. But yeah, as you can see, you can definitely do different types of engineering. There's not really a straight trajectory into it. That's what happened to me. So yeah.
Thank you so much, Grace and Sinai. I'm amazed at all the experiences you've already had, even as undergrads, and already working in the field and starting to get a sense of what you might want to do moving forward. My background, I lived overseas when I was growing up, and I moved around to a lot of different places. And so for me, an interest in engineering came out of first, my father was an engineer, and we moved around a lot growing up. And I loved the idea that I could, with an engineering job, I could travel to a lot of different places and get to know a community and try to help it. So that was a big instigator for me to pursue engineering. I also had another love. I loved working. I loved physics. I really liked how physics is a great way to a tool you can use to model the natural world. And, as I've learned more and more about physics, I love gaining an understanding of there's so much we still don't know in physics. And so I think there's still so much to uncover. But I just wanted to talk to you today about a project I worked on as a mechanical engineer because it relates to our water lab today. As I worked and gained more experience as a mechanical engineer, I worked on a lot of different power plants. I told you I was in the power sector. And one project in particular, I was senior enough that I got to lead the mechanical design of a power plant. And that meant I got to see this design. It was just an idea on a piece of paper, taken all the way to construction, startup, and operation. So that was a really great experience for me. I traveled a lot the plant was called Sutter Power Project, or Sutter Energy Center, as it later became known. And it's located just outside Sacramento, California. And what's unique about this project, I'm sure you're aware that California has many progressive environmental regulations. They also have scarce water supplies, and they're wanted to be very conscious of using the least amount of water resources as possible. This plant was located in kind of a big agricultural area in the region. And so water was needed much more for growing fruit and vegetables than it was for operating this power plant. So our mission, our challenge was to design a power plant that had zero discharge, which meant no water. All the water that was used on the site needed to be recycled and reused. And so we came up with a design that instead of using water to cool the power plant, we used air. It was like these huge fans that would cool the water that was generated in the steam cycle, condense that water, and then reuse it. So an air-cooled condenser was a big innovation for this project. In addition, we had one of the most sophisticated water treatment systems around, so that the water could be reused and reused and reused many, many times in the cycle. So there were some challenges to overcome, but what was really cool as a mechanical engineer, I got to travel out to the site. I made sure that the mechanical design was progressing as it was supposed to. I had to make sure we were keeping on schedule and within budget. And then as we started to test the systems, I needed to troubleshoot when things weren't working very, as they should. And ultimately, I got to be there when the plant went online. So as a mechanical engineer, even though I worked in the power sector, I still was very much involved in water filtration and water reuse. And I wanted to, a couple of questions that came up just before we look at your designs, which have already been so great. I wanted to ask Grace and Sanahi to respond to a couple of questions we got from groups about in advance of today's session. And one this is from Burke Central School in North Dakota. And the question is, what roles do industrial engineers and mechanical engineers play in our water systems and to ensure water access in the country? And I know you're both, Grace and Sanahi, interested in mechanical engineering, but could you talk a little bit about that question, to answer that question?
Yeah, totally. So this is an awesome question. In terms of, experience that I've had through, coursework here as a mechanical engineer, there's actually a project that I'm working on right now, which is we're working closely with an archaeologist in Hong Kong who works at a dig site. And basically, when they dig up artifacts to clean them, they use a toothbrush and they scrub them. And it's a very manual, tedious process, and it involves a lot of water. And they're in an area where they don't have a lot of access to water, and they're struggling with that. And so what we're working on is, one, being able to automate that washing process. So making sure that they don't have to use toothbrushes anymore. We can help them clean the artifacts, but we're also making sure that we're filtering out the water and actually reusing it, given their, lack of access to water there. And so it's really awesome. We're playing around with pumps and different kind of filters, very similar to what you guys are doing. We're struggling, with filtering out clay, because clay is a very small particle, and we're working with, settling tanks and things like that to get rid of sand, and all those kinds of things that's found in dirt. But it's really, really important, and it's super impactful. I mean, we're hoping to, cut their water use down by like more than half, which would be huge for them. And really does make, a real world impact on people's lives and what they do all over the world. So yeah, that's just some experience that I've had with, water treatment and filtering. But Sinai, I don't know if you want to touch on anything.
Yeah, reiterating everything that Grace said, I think mainly mechanical engineers, I've done a lot of work with manufacturing certain machinery and wastewater treatment plants. So for example, there's a machine called the USB called the Upflow Anaerobic Sludge Kit. We don't have to go into the specifics, but basically what it does, it cleans all the water, makes sure it's nice and like clear and doesn't smell, doesn't have odor. And right now we worked on making sure that it was gravity powered, so meaning that you would need no energy. So essentially, communities in Honduras, sometimes they get power outages, they don't have sustainable energy sources. So mechanical engineers play in a role in that. So making sure that what they build, what they manufacture can work in these environments and through challenges. So definitely they have a huge role in making sure that everything is manufacturing and working correctly. So great question. I really love it.
Thank you both. And actually, Sinahi, you already touched on another question that I thought was amazing from a bunch of different schools, which are what are the biggest challenges in distributing water, especially to remote locations, and how are they addressed? Are you working on any initiatives to provide water access and ensure conservation to underserved areas? And it sounds like you did. Do you want to talk a little bit more about your Aqua Clara work?
Yeah, sorry, I think I got a little ahead of myself. So I guess mainly we try to really optimize the conditions that we might find in Honduras. So there a lot of communities, like I said, don't have energy, or it's very, very humid out there. So we also have to consider the weather conditions. So for example, as a remote location, we would consider lack of resources. So maybe they don't have certain materials that we would have here in the US, the lack of energy, and then the weather conditions or just the conditions overall. So I know my team went to Honduras this past, I wasn't able to go, but they went during winter break. And one of the community members was saying how sometimes it gets really, really humid that like the water tastes different. And as someone in the US that has the privilege of having clean water and all those things, you really think those through and you're like, okay, how can I solve that? So we're actually trying to figure out and make sure, although we are in New York currently, we're trying to imitate those conditions and make sure the water is clear. It has no weird taste to it. It can run fully gravity powered, so no real energy needs to be used. And no matter how hot it is, the machinery doesn't get overwhelmed. So having like cooling systems incorporated into it. So I guess those biggest challenges are like, you know, using the environments that we're not in, imagining it and being like, these are the solutions. So it's definitely more of a thought process, more of a testing phase. That's a lot required in engineering. So definitely are working on initiatives. We're incorporating more and more each day to make sure that communities do have the clean water access they can. But great question. I really love it.
Thank you both so much. Grace, I just want to give you a chance. Did you have anything you wanted to add? Any other projects that you've worked on that maybe had to deal with access as suggested in this question?
Yeah, I think just touching on the project I spoke about earlier, and Sanae had a great point of, putting yourself in the shoes of the people that you're designing for is something that's really hard, but really important. Because, what we think might be a good idea might be super not helpful for, that person and their conditions. So really, talking to those user groups and seeing, what is their need, and being able to address that really specifically is a really crucial part about designing something effective.
Such great points. Thank you so much. And I hope our teams today have sort of felt that a little bit of that empathy for those in the world who can't just go turn on the faucet and have a clean drink of water today. And you've seen kind of some of the steps involved in. It's not easy to get clean drinking water, as you've seen from your filters, but I've been so amazed with the designs you've come up with in such a short time. So with that said, can we see a few more of the designs? I know I wanted to give a shout out in my breakout room. LaSalle Academy was waiting patiently and didn't get a chance to show, and I was wondering if they could show theirs.
I think they are ready. I'm going to spotlight them for everybody. If they can unmute, we would love to hear from you all. We can hear you.
You can hear us.
Yes.
Great. We didn't get to present. We had a few different ideas going on. Hold on. All right. Who has the double filter? Larry, come over here. Just come over here.
Don't be shy. Come on up.
Two ideas. That's the camera. There. Okay, there it is. Tell her what you did.
Here we use two filters. we had for the bottom layer, we started out with the coffee filter and cotton balls, and then we went up to sand and rocks. But a consistency I noticed is that every filter that included sand, right? The end product of the water was always it was colored. So this is our filter right there. The water we started out with was pretty brown. Yeah.
Yeah, I was going to ask if we could see your starting water as well. Whoa, that's great. And what did you measure your turbidity at?
Dirty water. Everybody put their stuff in.
That looks pretty dirty.
Okay, we have one more, just one more. Come here, Hilton or Blaze. Come on, it's part of it. This one probably is one of our best ones as well. All right, this is Hilton. From that.
Yeah.
So tell her what you did.
First, we started off with the coffee filter, and then we added the rocks, and then paper towels on top of that, and then we added more cotton, and then paper towel again, rocks, paper towel, and cotton. Finish it off.
So no sand.
No sand. But that was the top.
No sand. And it was interesting that you noticed that the sand provided may have added some color to the water, but I also what I think I heard was you sort of had a double cycle of the filtration. Like you ran it through one series of levels and then you ran it again to sort of get that extra polishing effect, as my friend Miss McQuarrie mentioned. It sounds like a great design.
At first, it took a long time for the water to go through, but then it
was slow.
Yeah.
For all those layers. Okay.
Yeah.
Okay.
Thank you.
Thank you.
You. Well, we have a line of groups that want to share, and Burke Central was up next. Just so that you know, the order is going to be Burke Central, then International, then Girls, and then Megan's Classroom. So Burke Central, you are up. Let me spotlight you, and we can hear you.
So this is our water filter that we made. Okay. And I'm just gonna pour it in the trunk. It's very slow. Our water filter is very slow. But I started off, I used napkins. This is my second one. And then I went in with 8 cotton balls. And then after the cotton balls, I mixed the sand and the rocks together. And that's how clear the water turned out from this.
That's a massive improvement.
It is. Look at that initial water and the finishing water. Very nice effect there. Well done.
That's awesome. Was there something that you guys struggled with or had an issue with and then you changed it around?
No.
No. That's awesome. Good job.
Well, thank you so much.
Mini water bottle. Oh,
okay. Never mind you.
All right. Thank you, Burke Central. We are going to International Leaders in Texas. Let me spotlight you all. Can you unmute so we can hear you?
Hi, good afternoon, y'all. So we started off with this very dirty water. It was a mixture of a lot of the material we had on us. And we actually filtered it through 3 of our best filters. We started it with this one, and it came out somewhat cloudy. Then what was the next one? This one? Then we filtered it through this one, but the cotton ball fell in the process. But we filtered it through here, and then we left our final design, which is this one, which the water is almost clear. And as unsafe as it might be, we actually taste tested it, and it tastes better than the water fountain.
I love that. Can you talk a little bit about your transition between the filters?
Between the rocks and that's that.
So with all of these, we did layer by layer with the coffee filters, using each of the different materials, including the rocks, the sands, the cinnamon, and we did different processes with each. Like we started with the heavier, the thicker materials at the bottom with this one, then thicker on top with this one, and then we kind of did a spread out with this one to make it randomized. And it seems that transition from all the different types in different orders actually made it water way clearer. But we also noticed that the filters we had in class that were made that were quicker ended up with dirtier water. And those that had the dripping technique and were slower ended up with the cleaner water.
So you've hit upon a big trade-off. There's a big balance between flow rate and the clarity of the water, which you've discovered. And then there's a cost associated with that. Great observations, really good.
Fantastic. Thank you guys for sharing. We are heading over to the Girls Global Academy. Let me spotlight them. They are ready. Can you ladies unmute for us? All right, let's see if we can hear you guys.
It's all right. We'll get it. Hold on. What
We can hear you now.
Hold on. It's okay, y'all. All right. Can you hear us now?
We can hear you. Yes.
Excellent. Excellent. So this is our water. We use rocks, a cotton ball, the coffee paper, and the water bottle top with the cotton ball. This is how it turned out.
I like that idea of using a funnel for the water. Oh, and look at that initial starting water. That looks like a great improvement. But I like that you use the top of the bottle as sort of a funnel to help channel the water flow. Did that change your flow rate at all?
Yeah. Oh, okay. So we got a couple more. Hold on for 1 second. We got 2 prototypes. Okay. So so this was our before product, and this we did it again, but this is our second one. It seems to be more clear than the first one we did. So what we did it different was instead of just straight putting the cotton balls first, we put a coffee filter layer first, then we put the cotton ball, and then we kept layering it with the tissue and the coffee filter, and then we still rock and sand. Thank you for your time.
Great job. And I could see the difference. I just wanted to have one of our great ET environmental engineers just chime in really fast. Miss McQuarrie, you left something in the chat, but would you mind just talking about that briefly with the whole group?
Yeah, I was just so amazed to see all the different prototypes that we had. It was incredible. And we started to see those trends, right? We were seeing the patterns where maybe the faster the water was going through, the less effective treatment we were having. And that's one of the really difficult things we have to balance in water treatment, is because we can make really, really polished and perfect water, but if we can't treat it fast enough, then it's not really a good solution. And so in water treatment, then we start to add different elements, like maybe pressurized, so that we're actually pressurizing water as it's going through those different filters, or pre-treatment. So like we heard from our mentors, our student mentors, we can have allowing just natural gravity settling to happen, where we can kind of pre-treat our water, remove a lot of the bigger pieces before we actually start our treatment process. And if you guys are, any of you, looking for something fun to do in the classroom, you can also look at this as a 2-stage filter. So you have water that comes out of your first filter. You could add a second filter and try pouring that effluent through another stage and see what kind of a better performance that you could get. So great job. I love to see all these results.
This is fantastic. Thanks for hopping in there, Carla. And we're going to go to Shepherd High School in Illinois. They are ready to share. You guys have to unmute those so we can hear you. Yeah. Thanks for running to the computer. All right.
Okay, so this is our water, and we have like the filter paper, and then what like really helped us was we compressed like 3 cotton balls right here, and then we put some sand and then paper and rocks, and like the paper really helped, and compressing everything and pushing it down really helped. So.
And this is our before.
Mm-hmm.
That is amazing. That's quite a difference.
Mm-hmm.
Did you have
I think you probably saw a big result.
We didn't hear that. It broke up.
Sorry, I think I talked over somebody. Go ahead.
I was just saying, I noticed when we were going through that, when people were actually compressing their cotton balls at the end, was having a really big impact. So do you think that had a big impact on how polished your water is at the end?
Definitely.
I think
Definitely.
yeah. So it's not just the media, it's how we execute it, how we apply the media that makes a big difference.
For sure.
Yeah.
Well, thank you for waiting and sharing with us, ladies. We appreciate you stepping up. We have another group that is ready to share. So
Thank you.
Monsignor Farrell, you gentlemen ready? Can unmute.
Hey, how are you
Hey.
guys?
Great. Let's see what you got.
Okay. So this is the water that we use to put in the filter. And that's the outcome. Now, him, here. He helped in all of this. He actually built this. Yeah.
Can you hold them both up at the same time again? Perfect.
And tell us about your layers. What did you use? Because that looks pretty good. It's a little
Yeah, 100%. I'll leave it up to you. 100%. So we have a water bottle here, and we use rocks, sand, filter, cotton balls, cinnamon, and dirt.
So was the cinnamon and the dirt part of your filter process or part of your water? Yeah. Part of your water. Okay, yeah. Got
Filter
it.
process. I'm sorry.
Yeah. Got it. That looks great. What would you measure that turbidity at? What would you measure that turbidity at? In the lab, what kind of turbidity level did you give it?
About an 8.
About an 8. Yeah. Great. Well, great job. I really
Thank you. Love the project.
Well, thank you, Monsignor Farrell. I'm just going to make a shout out. I see that iPrep. Are you guys ready to share? They're all standing around the camera, but I don't see a hand raised. You guys ready to share? Thumbs up? No? I'm going to spotlight you guys. Let's see if they're ready. No, you're not ready to share? You guys can unmute and chat with us. Don't be shy. Hi. Don't be shy. They all want to be the camera. Don't be shy. I see you have a design there. You want to come up and share? No.
We threw ours away.
Who threw yours away?
No, I have mine.
You have one.
Angelica, bring your design.
Come on, bring them up and share with us.
Thank you. She's coming. Get fired. Don't even go. The mic is still on. Go. Please proceed, baby. Proceed. Again.
So I put a coffee filter at the bottom with a cotton ball like in the lid. And then I compiled like rocks and sand in layers, and I put cotton balls like in between.
That's great. So it sounds like you had a really good polishing level right at the bottom. Like you filtered it through coarser medium, and then you had your cotton ball and your coffee filter at the bottom. Nice approach. Thanks for sharing. Thanks for being brave and sharing.
Yes.
With us. Appreciate it.
Thank you. And we have another group that raised their hand and they are ready to share. LSA, I'm going to spotlight you and you guys can unmute. We can hear you. Hi.
Okay. I'm Kaylin. I'm Mia. This is our water. That was the water before.
The first water.
So, yeah, that's it.
Can you tell us about your layers, and did you try more than one trial?
We did. This is our second one. So our layers is first we put down a coffee filter, and then we put in a paper towel, and then we just packed in like a bunch of cotton balls, And then we kind of like
the rocks.
yeah, we went like kind of like ham with like the
fun.
rocks and the sand. And then we just poured in our water, this water.
It's very gross.
And then this is what we got.
It looks great. And how was your flow rate in your final design compared to your original design?
The original one went
both-
real fast.
yeah.
But this one was slower, definitely.
So
Yeah, and it looks pretty clear. So you kind of paid the price and flow rate for better clarity, which is exactly what Ms. McQuarrie was talking about. Well done.
Yes.
Did you have fun?
Yeah,
Oh,
so it was
we
a lot
had
of
so
fun,
much
actually.
fun.
Yay.
Yes.
That's very important too.
Thank you.
Thank you, ladies. Well, Joanna, I think we only have a few minutes here before our amazing keynote speaker is going to take over. So I'm going to pass it off to you to kind of wrap up the wrap up.
That's great. Well, I just want to say thank you to all the schools for your great participation today. I also really want to thank Grace and Sanahi for coming and sharing their backgrounds and their experiences with you. And also Ms. McQuarrie, our resident environmental engineer, who really has a long experience with these processes. I think that, as I mentioned, access to clean water is an incredibly important challenge for your generation to continue to work on. There's lots of great innovation out there happening, but I think there's more to be done, as you can see, and as you've learned today. And the technology is there for you to discover it. So I hope today you've enjoyed working as engineers, working in teams, collaborating, considering the constraints of the schedule and the materials that you have and the costs. These are all things, all part of the engineering design process. So thank you again. And you are going to have so much fun listening to this keynote speaker and learning even more about this important topic.
I see.
Yeah,
Sanjay is.
this has been an awesome presentation. I want to give a shout out to Joanna Carl just one more time. That presentation was outstanding. I mean, just the way that you related us all to clean water, the problem, you threw in a bunch of great nuggets on innovation. It was really, really good. I also want to shout out the students here. This team, as you all are presenting, we're catching some screenshots. I want to shout you all out and just show some of your great work before we introduce our keynote speaker. Shout out to LaSalle Academy. You all were kicking butt and taking names. Great turbidity as well. Great system.
Milton,
Maria Regina.
we're not seeing the pictures.
Uh-oh, you're not seeing? What are you?
No.
Uh-oh. Okay, let's see. Let me try this again. I'm just yapping along, man. Look at this great. How about now?
There, now we are.
Bam. Let me go back because I don't want to skip. I don't want to skip a school. We got so let me go back to the beginning. LaSalle Academy, great job. Great filtration system, great engagement. I also love, I love the outfits, man. You can't go wrong with everybody being in sync. Maria Regina, very, very nice. Love your engagement. International Leadership of Texas and Girls Global Academy. Girls Global showed us two different really, really nice systems. And International Leadership of Texas, you can tell they definitely put in the work, and that's very low turbidity water. So that's awesome. And then Shepherd High and Farrell High. So with that, I want to shout out the ET team. Joanna was excellent, and Sanai and Grace and Monica and everyone that supported in the breakout. And I also want to introduce our speaker. You are really, really excited to have Sanjay. He's an engineer, industrial engineering. He's an innovator and a leader in this field. He's been in something that's critical to this field, optimization. When you are limited on what you can do in innovation, optimization is really the way to attack this problem in the near term. He also is involved with nonprofits around energy and energy solutions. He's the chair of the American Water Works Association, and he has a bachelor's from the University of Auckland, and he works at Confluency. So without further ado, please give a big round of applause for Sanjay. So great to have you here, man.
Thanks, Milton. Looking forward to sharing some of my experiences today, and excited to be part of this amazing day. Just water treatment processes and everything related to water. I'm going to share some of my experiences here. Let me just share my screen. They're coming through okay? So I understand you've had an amazing day so far with just water treatment, doing the lab, having mentors and students, as well as experts talk. And so what I'm going to cover today is just a little bit more about how I got into water, why water is so important, and this is probably going to emphasize some of the other points that have come across today. And then overall, just want everyone to be aware of the challenges associated with water. So coming off the end of this presentation, just want everyone to really understand the importance and those challenges, because you guys are going to be the future of how this all comes out, and it's really important that that awareness is there, and that the new technologies, the saving the planet, essentially. It's the most precious resource on the planet, and without it, no one can survive. So I want to start off by just saying that when you think about civilizations around the world, first thing, the most important thing that they have to worry about, where they settle, is having a clean supply of water. And that's why you'll see lots of coastal areas being migrated to first, or areas around lakes, around rivers, where that clean water supply is. So it really is the most precious resource, and without it, you can't survive. You have certain places in the US or in certain places around the world that have to build the infrastructure to get the water to those locations. California, for example, is one of those. So it's really interesting to see where these settlements develop, how that water is getting there, but all about the equity and equality, and making sure that the cost of getting that water there compensates for people living in that area. So I just want to start with a little bit of a personal experience here. And I am of Indian descent. My grandparents moved from India to New Zealand, and I grew up in New Zealand, so I'm a second generation New Zealander. But when I was about 15, 16, probably the age that most of you guys are now, my parents took me for a trip back to India, back to the village that my grandparents grew up in. And this was their first time going back as well. So they were 35, 40-ish, and I was a 15-year-old. But it was eye-opening. The village that my grandparents grew up in was a place called Bordali, and that's one of the villages in the Gujarat state. But it essentially looks something like this. We have dirt floors, you have dirt roofs, the walls, inside the house, unfinished flooring. But probably one of the biggest things that stood out to me is that they didn't have a clean supply of running water readily available. When you get up in the morning, you turn on the tap, water comes out, you have a shower, you go to the toilet, you flush, and that water gets taken away. Think about all that infrastructure that goes on underneath, unseen, underground. And it's very easy to take for granted. When we were back in India, we stayed in this village for 2 weeks, and there were 2 hours a day at the start of the day when water was actually available. So you turn on the tap, fill up all your pots, fill up all your containers, store them away, and then that's the water that you have available for the day to drink, to cook with, to clean with, everything. And then obviously on top of that, you then have to boil it to make it drinkable. You have to boil it and heat it up to make it the right temperature for a shower. You then, if you're cooking with it, you then have to boil it and then use it in your cooking. So it's very easy to take for granted the situation that we have here in the US that most people are accustomed to. And if you think about going back to parts of the world that don't have that available, what would your life be like? So don't take for granted. Thankfully, my grandparents had the foresight to understand that India wasn't developing at the same sort of rate as a lot of places in the rest of the world. They migrated to New Zealand, and so I grew up in a developed country similar to the US, where you have that clean supply of water. And you can thank the engineers, the people who have developed these cities to have the infrastructure in place to allow us to do that, that the quality of life is so much higher. You don't have to go to the river and pick up water and carry it back at the start of the day. You don't have to prepare in advance to make sure that you've got your water supply for the day and then ration it out. So I grew up in New Zealand. I went to the University of Auckland and did a Bachelor of Engineering and a Bachelor of Commerce. I have lived in Belgium for a few years, and I lived in the US for about 8 years. Now I live back in New Zealand again from the last couple of years. But what I want to get across here is that the engineering degree is very versatile. It's taken me to different places. It's allowed me to work on different projects. These locations that I moved to weren't for work purposes that I was sent there. They were personal experiences that I've been able to experience around the world and get a good sense for different cultures, how things work. But all doing engineering work while I've been living in each of those locations. Engineering is such a broad degree that it covers, well, water is just one very small piece of that. Within water, you have so many different disciplines, and it just branches out. So the thing that got me into engineering was my love for maths, physics, sciences, and I didn't really know what an engineer was. And what I really like about this Engineering Tomorrow program is the awareness that it brings to what an engineer actually does, what these sciences and biologies and chemistries and all of that, how you can apply that in real world applications. And I wish I'd had something like Engineering Tomorrow when I was going through the school system. It would have helped me identify sooner what I'd be interested in doing. So I really encourage you to make the most of all these different programs that Engineering Tomorrow has available. So what I do now, I am the CTO of Confluency. So I started a company with a co-founder about 4 years ago, and we do operations and capital planning for these underground networks that distribute clean water and collect the dirty water for treatment. So it sounds very broad scale, but if you think about a simulation model or an underground network, the representation of that network, a digital representation, and the ability to run iterations and permutations across that, all the different inputs that go into it, water demand, where it's coming off, the operation of the pumps, the treatment plants, all of that. While you've got it all in place, you have development processes that go on. You have to cater for new areas of the city that need water. You need to cater for replacement mains. You have to operate that on a daily basis. So what we do is we help with a lot of those operational processes, optimizing them, capital planning, but all to do with that underground network from a city perspective. And so the underlying fundamental thing that we really do is we help solve and identify problems. And that's to do with the world's most precious resource. So that's what really inspires me. Not taking for granted what goes on underneath, but the fact that when you turn on your tap and when you flush the toilet, that water comes, it gets taken away. And there's so much that goes on behind the scenes that we're left not to have to deal with. So, and so I've mentioned that water supports all forms of life. It's necessary. But the cool thing about it, it has so many aesthetic benefits. You think about waterfalls, you think about lakes, you think about beach houses. They're all located and they revolve around water. You have fountains in the city. What are those? I mean, the fountains, they serve a purpose because they have water around the place, but you get, they're just nice to look at. So it's, you go to dams and you go visit dams, and the mass of water and the amounts of water, it's just an incredible phenomenon. So while it supports all forms of life, got to make sure that we protect it as well, because it has so many benefits for quality of life throughout the world. So I think that has been covered a little bit in some of the earlier presentations, but just want to emphasize that we have a finite amount of water in the world. It goes from different locations, different forms of storage, the clouds, it rains, but essentially the amount of water that we have in the world doesn't change. It goes from different forms, it goes to different locations. It's what we need to worry about in terms of droughts, in terms of supplying cities that have been developed, is that when it evaporates or when it rains, it comes and goes in different locations. And so that's when you have localized areas in the world that might start having problems. And a lot of the things that I'm going to cover just in some the example projects that I've been working on just help to deal with preciousness of that water. They help to deal with what we can do to help make sure that situations, emergency situations around the world where water is not available or there's a drought, how we can cater for those, but just understanding that we need to protect the environment. So in all those processes, when water goes from different forms to another, goes to different locations, snows and rains in different locations from when it evaporates, you have a water engineer whose job is to first start with the supply of water. And these 6 points here are really defined disciplines of a water engineer's role. So while I said the engineering scope is broad, very versatile, you then get into very detailed understanding of some of these concepts, and important throughout the entire process of just the water process of the supply. So making sure there's resources that are available. So back to civilization, when cities get developed, got to make sure that supply is available, that there is emergency backup, that where water falls, it's able to be retrieved. The treatment process, which is what you're focused on in your lab today. And there are some really cool concepts with new technologies for treating the water. You have certain places where the water filtration process, like what you've built, a gravity filter essentially, is not actually available because the water needs to be cleaned. It might be salt water from the ocean, for example. You might need a desalination plant. So areas where you might need more energy. Talking about the conveyance, so there's another role of the engineer. So once you treat it, think about getting that out into the system. There's a huge amount of piping, underground networks, pumps, reservoirs throughout the city where water has to get to the right places so that when you turn on your tap, you have pressured water coming out and available to you. Then that water goes back down the drain. You have rain. All of that water somehow has to get collected, otherwise you're going to get flooding. And then the whole concept of recycling. So certain places in the US now have grey water, for example. When you flush your toilet, it doesn't have to be completely clean. So the water doesn't have to be cleaned to the same standard that you're drinking. So you can have grey water that can be used to help flush. And that requires less of a treatment process, which then helps the environment because you're not using quite so much energy. So there are some very detailed parts of this, and I only cover the conveyance network and the collection part. But from an operational perspective, there are so many other disciplines that need to cover the other processes, and you can get very technical in amongst all of them as well. So now I want to cover just a couple of example projects that I've been working on. And this helps give us a sense of what an engineer does. One of the biggest lessons I've learned, and I'll come back to this at the end as well, is it's not just the technical aspect. There is so much more to an engineer's job than just the technical math equations, the simulations, the programming, all of that. It's bringing that together, things that matter, trade-offs, the costs, society, thinking about human health or human emotions, which is a little bit harder to measure. But all of that comes into play when you're helping to make these decisions. And just the best technical solution can't always be applied. Going back to your lab today, for example, you can put all the media in there that you want and get it much cleaner perhaps, but there's a cost to that. Not every city in the world or not every location can afford that cost. So you've got to take these things into consideration. So I want to talk about the picture below is the Blue Plains facility in DC Water. And it's one of the biggest wastewater treatment plants in the world. So we're talking about collection systems here. So you did the treatment process, which is clean water getting distributed out to the system. This here is a collection system. And where dirty water gets taken to be treated, the dirty water that goes down your drains, that comes off, runoff from the streets, rain, all of that gets taken away to get treated, put back into the environment. From the environment, it then gets taken and put into your treatment process for distribution. So we're talking about the first part, the earlier part of that cycle of that wastewater getting treated. Now, this wastewater treatment plant, it's one of the biggest in the world, and you can see the size of it here. It's on the edge of a river, and it's prime real estate, if you think about it, for these beach houses, for certain locations. But it's so fundamental for the entire city to operate. You can't have clean water, you can't have dirty water going back into the environment. You can't have dirty water just sitting on the streets because it affects the health of everyone, so the quality of life. Yet they had to build it on the edge of the river because it discharges into the river after it's been treated. So those are some of the trade-offs that you have to think about when, from an engineer's perspective, the ones who are designing this and thinking about the city perspective, thinking about the cost, all of that has to come into consideration when they decided to take up this prime real estate with a wastewater treatment plant, which is essential for life. So what we were doing for this is trying to understand, we didn't do it specifically for this Blue Plains facility, but for a wastewater treatment plant, we're trying to understand what areas of the system could you reduce the amount of wastewater going to the wastewater treatment plant. So you think about all of this rain or dirty collection system water coming in from houses, going into an underground network, and that water then gets taken to the wastewater treatment plant that we showed in the picture just above. That wastewater treatment plant treats the water and then discharges to the environment, or if it's above capacity, it has to overflow, which is semi-dirty water. And there are restrictions in the US which mandate that utilities or wastewater utilities around the US have to build their facilities or build the capacity of their system to make sure that they don't have that they don't go over a certain amount of overflow, or they call it CSO, combined sewer overflows. So this all comes into play when you're starting to think about the system. So under normal circumstances, you've got under normal circumstances, you've got water going into the system, the pipes fill up, potentially halfway maybe, and they call dry weather flow. That goes to the wastewater treatment plant, and then that gets treated and put back into the environment. Now you think about rain that might fall. So now you have your base dry weather flow from the households going into the system. rainwater falls throughout the system and those pipes get a little fuller, that water goes to the wastewater treatment plant, but the wastewater treatment plant only has a certain capacity. So it treats what it can, and then it might have a little bit of overflow above capacity, which is going down to the bottom right. So what can you do about it? You can increase the capacity of the site. You can take up a bigger footprint. So we showed in the I showed in the image above how much space the wastewater treatment plant takes up at the moment. But what if you made that bigger? You could then treat it. And you could, so when rain comes in, you can treat all that water and it gets discharged cleanly. So now think about that increased capacity, and now you have a bigger storm coming in. Now that increased capacity still overflows because it can't cater for that additional rain. So these are the trade-offs. You have to understand the frequency of these storms, what's allowed, what size treatment plant can I build, and what infrastructure can I build to avoid flooding, so allowing it to get through the pipes all the way to the wastewater treatment plant, and then trying to minimize that capacity or environmental damage, essentially. The thing with the increased capacity, which I didn't mention in the previous slide, is that what if the residents of that city can't actually afford to pay for it? So there's all these equity things that go into play when making these decisions, and it's not as clear cut. It sounds like a simple problem, but when you start getting into all the details and drilling down, there's good reasons why decisions are made. And a lot of very smart people are involved with trying to make these decisions. So from an outside point of view, it can be criticized by saying, well, why don't they just fix these pipes? But if you're not fixing pipes, you could be increasing the capacity of wastewater treatment plant. If you're not increasing the capacity of the wastewater treatment plant, perhaps you could be doing other things. Transportation, for example. So there's all these dollars that are competing. All these dollars that are coming in from ratepayers that have to be distributed amongst all the services that are available, water being one of them, but those are the engineering decisions that come into play. So bringing that technical knowledge combined with the understanding of society and what's actually available. So then think about this perspective where you've got rainfall, additional rainfall, and the increased capacity. What if there was a way to stop the amount of rainfall or reduce the amount of rainfall getting into the system? You have the same size storm here coming through. What if the amount of rain that got into the system was a little bit less? You could keep that wastewater treatment plant at a lower capacity, so you didn't have to build a bigger footprint, and you can treat it all. Ways of doing this, you could think about green roofs on houses. Think about green infrastructure, so gardens embedded into part of the city, which absorb the water instead of allowing it to go down drains. And this was the work that we were doing for a wastewater treatment plant and a utility to understand they didn't have the capacity, or they didn't have the funds to be able to expand the wastewater treatment plant. They didn't have the space to upgrade that wastewater treatment plant, yet they had a mandate that they were overflowing too much. So what other measures could you put in place? And so the study that we're doing, when you've got a simulation model of this entire system, you can then understand, okay, well, what if the amount of imperviousness, or what if we could absorb a lot more of that water further upstream in the system? How does that impact how much water ends up getting downstream? What if we build green infrastructure here? What if we incentivize customers or ratepayers to put green roofs on? So instead of the water falling,
without pulling you out all day, what?
Instead of having the water fall onto the roofs of houses, go down the drains and into the pipe, the roofs themselves absorb some of that water. You get the aesthetic benefits of a garden, the green aspects. You get less water in the system. That money that could be used to spend, instead of building out the wastewater treatment plant, could be used to help put towards ratepayers, so that you get the aesthetic benefits as well as the reduced need for infrastructure. So those are some of the trade-off decisions that I really that we've been working on that you can do with some of the new technology and digital aspects of having a representation of that system. Another project that I really enjoy, and this has probably been my forte of my career so far, I've assisted with energy costs. So I want you to imagine how much water you use each day. And on average, that's going to be about 100 gallons. And I don't know if you have a good appreciation for that. So in this bottom picture here, that is how much water that the average American uses each day. Think about having to go to the river, filling it up, and then carrying that back to your house so that you could use it. And then you think about every resident in the city going to do that. And the amount of energy that it requires, the amount of work that it's going to require, that's needed in some locations in the world. People have to go carry their own water back to their house. And water is extremely heavy. Just try and pick out one of these barrels, 100 gallons. It just gives you an appreciation for how much energy is used in these underground networks to get the water from its source, treated, and then pumped around the system to where it's actually needed. Those energy costs are usually the second highest cost for a water utility. And understanding the pump operations, understanding how you can leverage some of the incentives that energy being used at different times of day, like overnight, knowing where you have storage in the system that you can distribute to, reducing the amount of lost water or leaks in the pipes, all of that impacts energy costs. And so there are ways of optimizing the system so that you can reduce those energy costs for the pumps that are having to operate to distribute around the system. The hydraulics, this is where it gets really, it sounds like a really geeky problem, but not the way that I'm going to explain it, but it's a really cool, interesting problem because you've got water hydraulics, pressures, flows, pumps operating on their pump curves, you've got energy costs. You've got water that needs to get to different parts of the city at different times of the day because of the usage. When you get up in the morning, most people have peaks at the start of the day before they go to school, before they go to work. And then in the evening when they come back. So water utilities have to cater for all of this, but the hydraulics and the maths and all of that that goes on in the background is an amazing problem. And it's a really hard one to solve because of the different permutations and combinations of them and being able to optimize. But getting a handle on energy costs is a really important part of what we do with these simulation models and machine learning and some of the new digital technologies. But really, when you use water, when you turn on your tap, think about the energy that it takes to get there. Think about having to carry that amount of water to from wherever the source is in your city, which could be hundreds of miles away, to where you actually need to have that water available. And now I also just wanted to touch on some of the issues that can occur if developed countries in the world, developed cities, if that water is not managed carefully or if there are not backup plans. Cape Town water is one of these examples, but more local to the US, the Flint, Michigan issue, for example. But I'll talk about this Cape Town one because it happened back in 2018, 2019 timeframe. But the entire city ran out of water. They were down to about 6 days before the reservoir, before it rained, thankfully, in the right locations to fill up the reservoirs, and the city got back into the procedures. But 6 days away from the entire city running, that could have been catastrophic. Like, you imagine a developed city here, if you weren't allowed to turn if you were turning the tap on and nothing came out. So they actually had to have people lining up for water, ration that water, to try and prolong the supply that they had available, hoping for rain. And leaving fate to hope is not a great way of dealing with things. So how did this eventuate? it eventuated because they didn't have a backup or redundancy supply for the entire city. Now, engineers are frantically working to make sure that's available, and the reservoir levels are higher in Cape Town. So they got through this crisis, thankfully. But it highlighted points around the world that what happens if your main supply of water starts running dry? Do you have a backup option in place? Do you have a tunnel? Do you have major pipes that can supply the city in the event of a failure? Again, it comes down to the amount of money, equity, trade-off, trying to understand, well, if you don't, do we have enough money to build this? How important is that resource? How critical, what's the risk of rain not falling in the area, or the risk of your current supply getting broken, or the major pipe that brings water into the city going down? These are all things that need to come into play when you're making these engineering decisions as well. I was, at the time this crisis was happening, I met a Cape Town resident who came to the US for a conference, and he was explaining that he was in the thick of it all, and he's a water engineer as well. But he was saying they implemented measures such as after having a shower, or when they had a shower, instead of letting the water go down the drain, they would put a tarpaulin or a little piece of plastic at the bottom of the shower box and shower, collect that water that they were showering in, put it into a cylinder or keep it. And that was essentially dirty water, but not really dirty. And they were using that to flush the toilet. So instead of the toilet being connected to the water supply mains, they were picking up that water that they collected from the shower, putting it into a container, and using those containers there to fill up water. And this significantly reduced the amount of consumption that residents needed to use, which brought them a bit of time. And all of those measures in place probably is what led to the existence of Cape Town now. 6 days, you have all these measures in place, and it all came down to 6 days. Every little bit of that helped. And so he was also saying that they were still implementing that even after the reservoirs were all fuller. They didn't want to get into that situation again. They didn't want to be lining up for water like they did here, like in India, for example, when you're having to line up for the tap at certain times of the day to make sure you've got your supply. Imagine your developed city that you're living in at the moment having to do that. So all these new measures came into play for Cape Town, but all around the world, to make sure that they have this resiliency and redundancy and backup in place. So just rounding up now, the lessons learned. For me, I learned it a little too late in my career, while I was on the job, that I thought it was just the math, the physics, the technical side of things. But really, it's that bigger overall picture of how all that fits into society, all the trade-offs, presenting the right information, knowing what information is critical for making that decision. And that's some of the harder parts and the softer skills that, being an engineer, you start to learn and start to appreciate. And all the overarching goal, can that translate to make lives better? I'll hand it back over to you, Milton.
And that was really, really good. Great presentation. I love your story. I love, the innovative approaches and even the optimization that you're using. I guess one of the questions I had is, we're just so blessed with access to clean water, and I take it for granted every day. How do we get the word out? How do you get someone like me, others, to really appreciate this problem and get involved?
Yeah, that's right. Other than making the city run dry of water, right?
That is a way.
Yeah. I think whenever cities sort of run into drought problems, the word gets out very quickly as to how precious that water is. But you don't want to get into that situation to start with. The case of DC Water, George Hawkins, who was the CEO of DC Water, he led it for 8 years. He's no longer there, but he pretty much transformed that water utility. And a couple of the things that he mentioned when he after he left DC Water was when he first started, everyone had no awareness of the underground networks. DC Water had issues. There were people out on the streets fixing things all the time. Ratepayers were having to pay for these services that they didn't even know what DC Water were doing. So he's got one of the best transformation stories in the US, where essentially he made everyone aware by changing the logo, promoting, like you see ads all over the place in the city, promoting it like it's the commodity that it deserves. You have soft drinks or you have other things that are getting sold on these billboards, but he had water up there. He made sure that the people that were working around the streets and that ratepayers were seeing, he made sure that they were all wearing DC Water gear so that they knew exactly what they were doing, what the services they were paying for. So I think he's got one of the best stories about making sure that there was awareness and that everyone knew how important that utility was. It'd be great if other cities sort of were able to emulate that as well. But I think as an engineer, the basic understanding and awareness of it is really critical. And I think that's what the students, the fact that you're all part of this water lab today, or water treatment day today, is really promising. And I also just want to mention that the questions that were sent through in advance, I wish I had the insight and the maturity of what you've been sending through, of what you had sent through back when I was your age. I don't know, it's a really promising sign, the fact that everyone's here today doing this water treatment day, and those questions that came through in advance. I was very impressed.
Yeah, they are wonderful questions. I don't know if I ever would have had questions like that as a high school student, right? That maybe that shows that, you know, there is an impact and people are learning that this problem is important. One thing I wanted to talk a little bit about is innovation. And I think there was a question from the students that talked about the impact of artificial intelligence and machine learning in solving this problem. You have some experience in that. Could you speak about that a little bit?
Yeah. So the cool thing about machine learning and artificial intelligence is that it's a big hype, not hype in a bad way, but there's a lot of knowledge. It's being talked about all over the place about how things can impact. And in reality, it's been around for a little while. Just the applicability of it and the ease of being able to access, have it impact your lives, is now just being made more and more prominent. So the fact that it's been around for a little while means that it's been embedded in some of these processes already. That sometimes behind the scenes, you get machine learning and artificial intelligence that's actually helping. And because of these underground networks, the operations of the systems, you may not see it all the time, but there are little aspects that are getting into play. The fact that it's now becoming more and more spread and easier to use, there are a lot of engineering firms, a lot of the technologies are now making it a bigger part of what they're doing as well. And when you start getting into, there's a lot of decisions that get made on a day-to-day basis from operations. There are a lot of these underground network models, digital representations of things. You can start using machine learning on those and leverage these capabilities more. So the foundations are all there, and it's now enabling the and identifying where this can really help. But I think there's a lot of promise associated.
That's awesome. Why did you say yes to this event? That's a question that came up. Why did you say yes? I was living in DC at the time when I found out about Engineering Tomorrow, and I was working in a water engineering role at the time in Alexandria, and the idea of Engineering Tomorrow, and I got asked if I would help to lead some of the labs, and I didn't even start with the water treatment, but I then got very
very interested with what was going on the water treatment side, just because of my water knowledge. And then it made me realize, it's like, I never had this opportunity when I was a high school student. I think I mentioned that. It would be really cool if like I'd had that opportunity and learned a lot of what I know now about what engineers do about water, about how the subjects that you're doing in school relate to the professions that are out there at the moment. And so then when the opportunity came about, I'm very honored to be asked to be the keynote for this. Water, one of my I'm very enthusiastic and very passionate about the challenges, the understanding of it, and I work in it day to day. The ability to kind of get the word out a little bit more and help students that are trying to make these tough decisions on where to go for universities or what. I thought anything that could help that would have made it easier for me. I think it's a really good cause.
Excellent. Another great answer would have been Constance, right? Constance, she
I was going to say Constance and Tim.
Okay.
Yeah.
Great answer. Joanna made a comment when she was presenting that access to clean water is a basic human right. You know, it doesn't always feel that way. I mean, even outside of what can we do to influence globally and in countries and municipalities to ensure that everyone gets access? What are some things that could be done?
Yeah, I think just knowing that it's not available to everyone in the same way that it's available to you is the first good start point. And then once you're aware of that you start to get a little bit more appreciation for what we have in developed cities, I think then it sort of comes a little more naturally that people start volunteering for these really good causes. They can do overseas experiences, for example, that not just get to see a different culture, but also help build up some of the knowledge that you get from a developed country, take that to areas where they're really struggling. And so there's all these new initiatives and projects that are non-profit organizations that now help with collating people with these skill sets that want those experiences at the same time. Those are ones that I would highly recommend getting involved with. And my wife did a trip to Honduras when she was back in studying, and she convinced her family to do the family trip down there to help with water supplies in the schools and everything. And so instead, I think her parents asked her where they wanted to go for their family vacation this year, and that was her idea to go down there because she knew, she was aware of some of the areas that needed the issue. You could see something very different, a different style, culture of the world. And when you go see those places, you appreciate that the people there are still content. Like they're living life to the fullest. They're making the most of everything that's available. And you can do that. And you can understand then that if you can make a small change to their system and bring some of the capabilities that you have there, how much of an increase in lift that would be. But the benefit of that is that sometimes they don't even know what that lift could bring you. So it's the double element there.
Yeah, it really is an engineering problem. So how do you address, like you have a new city, right? How do they assess the water supply needs for a new location?
Yeah, so I think it comes before that. That let's take a developed city in the US. If you don't have enough supply, then you can't build out the development. So I think it comes in that decision that you have a certain amount of supply available to the city. You obviously always have the option of building these big pipes from different areas of the country or different regions into that area. But can the city afford to do something like that, what are the benefits of having this extra development or this new part of the city available versus the cost of bringing in that extra water supply. So there are some parts in the country that have the luxury of having that excess supply of very clean water. New York, for example, like completely gravity fed from a fresh lake, so hardly have to treat any of it and don't have much energy costs because it's all gravity supplied. So that's a city that strives at the moment. I like to think it's partly because of the water supply, but there's obviously a lot more going on as well.
Excellent. Excellent. So you have been, I guess, coming from like your background, coming from India, where there was, your region didn't have a lot of access to water. It seems like you were born for optimization, right? Talk to us about optimization in engineering.
Yeah.
I don't think people appreciate that term and how it applies to all facets of engineering.
Yeah. So the way that I explain optimization is that engineers or anyone doing their job is usually going to optimize the output somehow. You're going to be possibly presented with a few choices of how to get to that solution, and you're going to choose the best one. So essentially optimized, right? Optimization, from my point of view, is a more structured approach to being able to solve a problem. Algorithms, for example, machine learning, all of these different technologies that go into optimization. I think optimization is an overused word, whereas really I consider optimization to be the actual programmatic, or that you can use specific algorithms that drill in and try and come to a solution out of a combination of hundreds, thousands, millions of potential solutions. So, and that's because of the world that I come from with the simulation models and the optimization that we're talking about. So when you say optimized, I would like to think of it as more of a more comprehensive approach and understanding. So rather than just the 10 manual solutions that you might be able to come up with and choosing one of those, hundreds of thousands, making sure you've got that really holistic understanding so that you can justify these decisions that are being made.
Wow, that's really good. Here's my last question. I was looking at your LinkedIn. I learned you used to be a hockey coach. Is that right?
Yeah, field hockey though.
Okay. Okay.
Not on ice.
What do you do in your free time? Like, how do you de-stress? How do you enjoy yourself?
Yeah.
What do you do in your free time?
So I'd like to say that my 3 daughters de-stress me, but they don't necessarily de-stress me.
Oh, okay.
They're very enjoyable.
It can be a little of both.
Yeah, that's right. I have a 6-year-old, a 4-year-old, and a 3-month-old.
Wow!
So
Congratulations.
Thanks. They keep me very occupied, but I really enjoy the family time. And if tying that in with some of the hockey side of things, I like taking them outdoors. I like taking them bike riding. I like taking them running. I like giving them experiences that I like doing, trying to present them options that will open them up to being able to decide for themselves in a few years' time.
That's great. Really, really good. Well, thank you so much for this awesome presentation. I really caught some good nuggets from this, that this water problem is an all hands on deck issue, and it's an interdisciplinary challenge. Every field of engineering needs to be involved and can be involved. Also, solving problems that matter. I mean, with a resource so relevant yet so scarce, it's nice to know that engineering can help address this challenge. You also talked about balance and priority. Like, not all water needs to be at the same level of cleanliness to address an issue. So you can really attack the problem that you need to attack. And we're doing this to make life better. And in optimization, you optimize the output. I like that. It's really nice, right? So can we give it up again for Sanjay, the Chief Technology Officer of Confluency? Excellent presentation, relevant subject. Thank you for your time, and we can't wait to have you here with us again. You got to do this again, Sanjay. I want to shout out all the students and their excellent engagement. You all were kicking butt. You're engineers today. Keep engineering in life. And last but not least, one more shout out again to Joanna. She did a great job just ushering us into the subject. Sinai and Grace and Monica and the entire team. It's been an excellent day. Thank you all so much. And I'm going to hand it off to my buddy Monica, the hostess with the most, to talk about next steps.
Well, I want to say thank you, Milton, for engaging us this afternoon, for all the teachers who made this happen. I have to say, we had some amazing teachers who went above and beyond for their students today. But just a reminder, your work is not done. We need your exit tickets from teachers and students. Don't forget that. It's really important. We really look at that. And we have our next event coming up on March 14th, our Astrodynamics, which Milton Davis is going to be leading, right? Yes.
Yeah.
So I hope that if you are not signed up for that, you sign up for that soon, and we will see you next time. Thank you all for joining. Fantastic job today, everybody.